All right, today we are time traveling back to 1976 to dig into a really fascinating paper from the MIT AI lab. Now, its title alone sounded like a complete contradiction, but it promised to bring together two totally opposite worlds of computer science. Let's see how they did it. So the paper kicks off with this kind of mind-bending question. What if all the basic tools that programmers use every single day, loops, variables, that infamous Godot statement, what if they weren't really fundamental at all? What if they were all just clever disguises for a single, much, much simpler idea? That's the puzzle we're going to unpack. To really get why this was such a big deal, you have to picture what programming was like in the 1970s. The whole field was basically split into two different camps with two totally different philosophies. It was a real battle of styles. So on one side, you had imperative programming. Think of this like giving someone turn-by-turn driving directions. Go here, turn left, change this value, jump to that line. It's all about a list of commands that change the computer's state. And on the other side, you had applicative, or what we now call functional programming. This is way more like just giving someone a destination address and letting the GPS figure out the route. You just described the what, the final result you want, as a sort of mathematical recipe. And right into the middle of this whole debate step our two protagonists, Guy Steele Jr. and Gerald Sussman. And with this paper, they didn't just suggest a truce. No, they proposed something way more radical. That one side of this war could actually be built from the ground up using the tools of the other. It was a totally wild idea at the time. So what was their secret weapon, the master key that could unlock this whole thing? Well, it all comes down to a beautifully simple and elegant concept called the Lambda expression. A Lambda expression is basically a function without a name. It's just a pure, self-contained little package of logic. The cool part is you can treat it just like data. You can pass it to another function, you can store it in a variable. It's like a computational recipe that you can just carry around and use whenever you need it. And this right here is the absolute key. Steele and Sussman figured out that this one simple tool was all they needed. They basically set out to prove that they could take all those clunky, old-school imperative commands and just rebuild them, one by one, using nothing but these Lambda expressions. Let's see how they pulled it off. All right, so now we're going to roll up our sleeves and walk through the paper's own examples. We're going to see how they took the classic way of doing things and translated it into their functional language, which was called scheme. This is where the magic really happens. First up, the most notorious command of them all, the goto statement. For years, programmers used goto to just jump from one part of the code to another. It was powerful, sure, but it almost always created what people called spaghetti code, this tangled, impossible-to-follow mess of logic. Now, this translation is just brilliant. In the Lambda world, each label, like L1 or L2 in the code, it just becomes a function. So a goto L1 isn't some crazy jump across your code anymore. It's just a simple call to the function named L1. And just like that, the tangled spaghetti code becomes this clean, predictable flow of function calls. The messiness just vanishes. Okay, next up, variable assignment. I mean, this is the bedrock of imperative programming, right? You compute something, you store it in a variable so you can use it later. Here, they're calculating some roots and storing them in root 1 and root 2. Seems pretty fundamental. Well, the Lambda approach totally turns this on its head. Instead of storing a result in a variable, you just pass it directly as an argument to the very next function that needs it. You can see it right there. The values get calculated and then immediately fed into the next function as a parameter. The whole idea of a separate storage step is just gone. So there's the secret sauce, this brilliant little trick. Any variable that changes over time, you just turn it into a parameter for a function. What used to be a sequence of commands changing the computer's memory now becomes a clean, beautiful flow of data, passed from one function to the next. So, now that we've seen how something like goto and assignment can be completely rebuilt from scratch using lambdas, we are ready for the big reveal. We're about to finally understand the deep, almost poetic meaning behind the paper's title. Just let that sink in for a second. Lambda, the beating heart of functional programming, is being called the ultimate imperative. How on earth can it be both the complete opposite of imperative programming and its ultimate form at the same time? And this is the point, and it's just so cool. The paper proves that the Lambda expression isn't just an alternative to those imperative commands. It's something way more fundamental. It's like a universal building block, a computational atom that's so powerful you can use it to construct the very commands it was supposed to replace. It's not just another tool in the toolbox, it's the raw material the toolbox itself is made of. Now, the paper takes this idea to its absolute extreme with a concept called a continuation. Think of it like this. Normally, a function returns a result, and the program just implicitly knows what to do next. With a continuation, you explicitly tell the function what to do with the result. You actually package up the what to do next step into a function that you can pass around. And check out this example. This factorial function, fact, it doesn't return a value in the normal sense. See, it takes an extra argument, c, that's the continuation. When it finally gets the answer, it doesn't return it, it calls c with the answer. This is so wild and means even the very idea of returning a value can be rebuilt as just another function call. Okay, so why should we care about some dense academic paper from almost 50 years ago? Well, because the ghost of this paper is living inside practically every line of code we write today. Its ideas didn't just win the debate, they became the air that modern programming breathes. Seriously, every time a Python developer writes a Lambda or a JavaScript developer uses an arrow function, they are using this paper's core idea. The superpower of closures, functions that remember where they came from, that's possible because this paper helped prove that functions could be treated just like any other piece of data. These aren't just features, they're direct descendants of this 1976 method. This quote from the paper's own introduction just sums up their whole mission perfectly. They weren't just playing around with theory. They were on a quest to find the deep, simple unity hiding underneath all the messy complexity of programming languages. They were looking for a common language that could explain everything. And you know what? They found it. And so that kind of leaves us with one last big thought. This paper showed that a whole universe of complex programming commands was really just a clever combination of one simple idea. It really makes you wonder, right? What other complex things in our lives, in technology, in society, are really just variations on a single, elegant idea hiding right there in plain sight?